Hello, my name is Danielle Marino, and I'm co-author of this project with marine science student Samantha Brayton and advisor Dr. Anna Pfeiffer-Herbert. And this project was funded by a grant from New Jersey Sea Grant. We conducted our research on estuary bottom type and nearbed velocities in Barnegat Bay, New Jersey. The bottom type of an estuary has a large influence on velocity of water flow within the bottom boundary layer of water, which is right above the seabed. When this layer contains large flow speeds, there will be more erosion, and lower speeds will cause more deposition. This layer can also be impacted by roughness elements such as seagrass, which can decrease the water velocity. Oyster aquaculture cages or gear can be a roughness element, so our hypothesis is that slower velocities will be found within aquaculture gear and vegetated sites compared to the bare sandy bottom types. In our first figure, we have a map of the study area, which is marked where each mooring is placed. Each of these locations has a different bottom type where data was collected. Data was collected in 2-week periods during the months of March and October using tilt current meter instruments at each station, which includes a sandy bare bottom site, a vegetated area, and an area with oyster gear present. Please note that aquaculture gear was not deployed with the instruments in March, but it was deployed in October, so the gear site during March doesn't have as large as roughness elements as it does in October due to the cages not being deployed yet. So in figure 2, we have an example of a time series over one tidal cycle in October. This is showing water speed in the along channel direction. Flood is the peak positive velocities and ebb is the maximum negative velocities. We see in the gear station that it has much smaller velocity values for both directions in comparison to the other stations. In figure 3, we have the mean peak velocities during the months of March and October during both flood and ebb. The bar height represents the mean peaks at each station, and each contains an error bar for standard deviation. The asterisks indicate a statistically significant difference in velocity between sites as a result of an ANOVA test during both March flood and October ebb. So this was also found that there was no significant difference in tidal currents at the bare and vegetated sites compared to the site containing aquaculture gear, which did show a significant decrease from an unpaired t-test. So there were differences in velocities across the sites, but not always significantly different, and when we compared over time between March and October, the only significant change was in the site that had gear present. In order for erosion to occur within the sediment of this area, we look for current speeds that are above or equal to 25 centimeters per second. So our fourth figure shows the percent of time that erosion occurs during both the months of data collection at each of the stations. The bare bottom site showed the highest rates of erosion. Lower values were recorded for the vegetated and gear sites, but there was a notable drop at gear during October compared to the March data due to the oyster gear not being deployed yet at that time. Tilt current meter demonstrates faster current speeds at the bare bottom site and slower speeds where gear was present due to the difference in roughness elements. Aquaculture gear will also cause more deposition of sediment compared to the other sites. More deposition allows for sediment to settle as well as other particulate matter, which can be substances such as seagrass seeds, causing more vegetation, which is a roughness element, and can further impact nearbed velocities.